Nikos Diamantis here today, and he's from the University of Nottingham, and he'll be speaking to us about some exciting recent work that he has on modular iterated integrals associated with cusp forms.
Yes, thank you very much for the invitation. I don't know if it is exciting, but it is new, at least. So I will start by describing a bit the context of the work, because some of those notions that are included in the title are relatively new, and they go back to work by Francis Brown. I will say a few things about his context, what the motivation for these constructions were for those definitions. That will be the first part of the talk, and then I will introduce the questions, and then just some new approaches to those questions and further problems. So I go straight away with the usual context, mostly to fixed notation. As we will be working almost exclusively with the modular group, which I will denote by gamma. And we have this notation of S and T for the involution and the translation. And we have also the upper half plane, which is the set of complex numbers with positive imaginary part. The next space we'll be considering, space of functions, which brings us closer to the title of the talk, is real analytic functions. Not all of them. We look at those that have some moderate growth uniformly in the real part. And moderate growth, we mean the y to the c. That's, I should say, possibly at this stage, that the more natural space where real analytic modular forms act and work is in the case of at most exponential growth, and which brings us back to work that many of you have already contributed to, with weakly holomorphic modular forms and so on and so forth. But this is the subject of another work, which will be briefly mentioned later on in the talk. We'll only focus on this moderate growth real analytic functions. Then we have a special case of that, which is the holomorphic functions, again with those conditions. And now I have this notation, which will not really be using, but I just mention it to give the sense that we can specialize even to cuspidal forms, cuspidal holomorphic forms, cuspidal real analytic forms, those that have exponential decay as the imaginary part goes to infinity. And that's the first part of the context. The second one is the action. The action, that's one of the most, let's say, obvious characteristics of this whole theory of real analytic modular forms, is that we have two weights, and what we do is we take into account the conjugate of z as well. So we have, as usual, f of gamma z multiplied by this j invariant cz plus d raised to the power minus r, but there is also a co-weight, as it's called sometimes, which refers to z bar. Now, this action by itself is not new, already has appeared in, we see some of those books by Maas where he first introduced his mass forms, and later on by a student of Marvin Opp. He also studied these two parallelly acting weights, but what makes it special is the definition, which I'm going to give right now. But in any case, that's the action we'll be working on, and then we will maybe specialize at s is equal to 0 and so on and so forth. We'll see it in action, but the notation will be slash with subscripts R and S. And if I want to go to slightly more technical aspects, we need the R and the S to be of the same parity, to be positive integers, and their sum to be at least equal to 4 for reasons which can be guessed. And then we extend the action by linearity. We'll see one instance where this will appear. So now we go to the definition, to the actual definition, and make some very quick remarks about the meaning of this definition. So we call a function f of moderate growth a real analytic modular form of weights R and S for the modular group if we have these two conditions. First of all, okay, that's easy to guess. We need invariance under the action which I defined before. We have these two weights, and it has the form. It can take this more explicit form we are considering here. And the second thing, and that's what makes the construction new, the Francis Brown's construction new, is this condition about the Fourier expansion. So we would like to have some kind of, we're in between the standard Fourier expansion which we encounter in holomorphic modular forms, but we don't go to, as let's say, exotic objects as in the case of mass cusp forms with a k Bessel functions, W Whittaker functions, and so on and so forth. We're somewhere in between. And the reason for which this has been chosen to work like that is, in the first instance, because this gives a very natural account of real analytic objects which are reasonable and not too wild, if you wish. We have the y, meaning, as I mentioned before, the imaginary part of z. We have this q, the exponential, and also its conjugate grouped together in this form. And also, in addition, this y appears more as a polynomial rather than a series. So it is a more specialized object. Where it comes from, why it was chosen this way, specifically in this way, apart from being natural, is from mathematical physics. Because Francis Brown has been looking at some problems of string theory and objects which go eventually to perturbation theory, and these were the expansions that naturally appear in this context. So there was this kind of mathematical physics background. But it seems that, as we'll see later on, it happens to be also very suitable for arithmetic purposes. So that's the first definition, the basic definition that we have. And yeah, I would like to ask if there are any questions, because in this format, it's hard to guess if there is some kind of confusion about anything that I have said so far. So if there is any question, I'll be happy to answer before I move on. Okay, so we continue with the notation of what we introduced. We denote by a calligraphic M with subscripts R and S, the real analytic modular forms of weights R and S. And what is important in this case, especially when we go to the technical details of what is happening, is that we take the direct sum of that. We need sometimes to look, actually most times we look at all pairs of weights in their entirety. There is some kind of gradient filtration taking place, actually various types of filtrations being imposed on calligraphic M. And that's a very special case. And if you wish, first examples of such forms, we have the Roman or italic in this font M sub k, which means the standard modular forms of weight k, and we have S sub k, just mentioned because it will appear fleetingly. It is S sub k cusp forms of weight k, which is the same thing except that we impose the exponential decay condition. Some more genuine examples of this construction. We start with almost trivial but important example of the imaginary part of z, y, which is an element of the space of real analytic modular forms with weights -1 and -1. That's already, as I said, a trivial but important, believe it or not, modular form, real analytic modular form. Already I have mentioned the special case of holomorphic modular forms as special examples, but what is equally important is the conjugate of holomorphic modular form, which lives in M, calligraphic M0K. Now, the real, let's say, serious and very, very fundamental example that we have, possibly even more important than its counterpart in holomorphic forms, are the real analytic Eisenstein series. So the definition is exactly what you would expect. Instead of taking 1 over R of gamma Z to the R, we take also the conjugate copy of that with a suitable power exponent, and this will live in MRS. And this is more important if we see it in the context of, again, Francis Brown's work on, actually, it was work which was done before even real analytic modular forms had been defined by himself, but he was working with such objects in the motivic setting using the iterated integrals of such Eisenstein series or combinations of other objects with regular Eisenstein series, which also require some regularization already done by Francis Brown. So they play a very central role in the theory, and one can get highly non-trivial results just by looking at this calligraphic ERS, the real analytic Eisenstein series on 2 weights. That's a fundamental example of elements of MR and S. The second element, and it's a natural question to ask because I already mentioned mass. What about the Laplacian? Because when I mentioned the definition, I compared it a bit with the Fourier expansion of mass cusp forms. But what is key in mass cusp forms is, of course, the invariance under the Laplacian. So in this sense, this definition is much, much more general than mass cusp forms because we do not require the eigenfunction of the Laplacian. So it is all real analytic functions. And if there is any restriction, and it turns out to be an essential restriction, is the form of the Fourier expansion. On the other hand, mass operators play an absolutely key role, and I would say perhaps even with some exaggeration, even more important and more complex than the one which is played by the Laplacian in mass cusp forms. So I will start with some definitions which are adjusted in the setting of two weights. We have the partial derivative, which is which what it does is it increases the first weight and reduces the second, and we have the bar, which plays the other way around, reduces the first weight and increase the other one. And their formulas are the familiar ones up to renormalizations, and they produce bigraded derivations on the algebraic sum over all weights, which for practical purposes we just denote by partial and bar partial by conjugate of partial, with the understanding that we see at which piece of the grading it acts, and then we choose the appropriate R which is involved there. So the next definition, which brings us closer to arithmetic, is a subspace of calligraphic M. And when we talk about calligraphic M in this case, we mean the algebraic sum over all weights. So we have some kind of perpendicular parametrization happening now. In terms of length, we have the weights, and now we have the lengths. So we start with this definition, which at first seems a bit peculiar, especially if nothing else because of the name, and it's iterated integrals, and we see no iterated integrals, or for that matter any integrals at all, but we'll see why they are called like that. So the definition is going to be recursive. We first define this trivial example, mi, this means modular iterated integral of length -1, to be the space 0. And then for the next level, for L is equal to 0, we define mi sub 0, modular iterated integrals of length 0, to be the largest subspace of our sum, which I translate these two containment relations, which are closed under the action of both the partial mass operator and the anti-holomorphic mass operators, the conjugate of that. So that's how it would read in the case of L is exactly equal to 0. For higher levels, we do the same thing, but we could interpret those relations, containment relationships, as saying that this is the largest subspace of our space of real analytic modular forms that are closed under the action of both the partial and the conjugate of partial, up to lower order terms, where lower order terms it means the products of modular iterated integrals of lower weight and polynomials of standard holomorphic or anti-holomorphic modular forms with coefficients in the imaginary part of Z. So that's maybe a way to interpret that. So whereas in the case of integer L is equal to 0, we have the nicest possible situation that we take a space which is closed under our operators, under our mass operators, we cannot always expect to have this best scenario. And then in other cases, we, if you wish, almost have that, except that we have to make some correction, some controlled correction by lower order terms, times polynomials of really classical objects and powers of imaginary part of Z. So that's the thing. So this is the largest possible subspace. It's a little bit of an existential definition, but we'll make that a bit more explicit. Something which I should mention, and for the purposes of our talk, will remain simply one of those footnotes that are of technical nature, is that I kept saying for brevity that we're looking at the space of real analytic modular forms, but actually we do not look at the entire space of real analytic modular forms across all weights. We look only at the non-negative weights. And that's actually crucial and it helps actually classify the spaces in low lengths. And but this is something to keep in mind, because we do need sometimes to relax a bit this constraint if we want to move forward and get more results. Okay, so why this definition? What is the justification of this definition, which, by the way, is also due to Francis Brown, it's not mine. As I said, part of the motivation for introducing such things is perturbation theory. And there are some words which I just repeat without knowing what they mean. Genus 1 string perturbation theory. That's something in mathematical physics, string theory. And what is possibly closer to mathematics is that there are some modular functions which are called modular graph functions in this string theory. And they have their definition, but now the things that we expect, and Francis Brown has given a lot of evidence that those modular graph functions will actually be modular iterated integrals. So not just real analytic modular forms in the generality, but that they satisfy the relations of modular iterated integrals. So that's the expectation. So that's the first element. And the second one is more number theoretic. There are two main pieces of evidence that these have some arithmetic nature. Elements of those spaces have some arithmetic nature, at least those that I'm aware of. It's the first one, which has been given again by Francis Brown, of motivic nature. There are some kind of pure motives and other motives. Again, I don't know much about those things. The one which I know a bit more about, because I have proved some results, is that you can define classical number theoretic invariance on such objects in a way that you cannot really do in general real analytic modular forms. So we're talking about things like L functions. L functions you can define in great generality. We have defined them on all real analytic modular forms. When I say we, this is joint work with my PhD student, Josh Druitt. But what is special for MIL, for modular iterated integrals, is period polynomials. And what we mean by period polynomials is some polynomials which encapsulate special values of L functions, of their L functions. And at the same time, they satisfy relations which, in a fancy language, we could say cohomological. They are cohomological, they are one cocycles. And at the same time, also, this can be done in a finite dimensional space, which is the space of polynomials. And it seems that it is only in those cases that we restrict ourselves to modular iterated integrals that you can have these classical objects that appear. And they can be a basis for even more precise results. Some applications have already been given about algebraicity relations. The moral of the story, that's the only thing I'm going to keep out of all that, because this is a different, that will be the subject of a different talk, is that this gives some kind of credence into the claim that the MIL, modular iterated integrals, have some arithmetic meaning. So this is just why we bothered defining and also defining them in this convoluted way. So now there are some other questions which I wanted to look at, more structural, but they're related also to my last slide about the arithmetic. So the first question which arises when you look at these objects of work that has been completed so far is that one looks at the MIL, but not at the entire space. The elements of this space that have been studied so far are those where it is enough to consider the Eisenstein series. And I already hinted on that, because I said that the Eisenstein series are perhaps even more important in the theory than in the theory of classical holomorphic forms. So, but one way or another, let's say the first three foundational papers by Francis Brown, they study only forms which would belong to the largest possible subspace of calligraphic M, that satisfy these two relations with the E, not the entire M, not the full space of modular forms. And the natural question to ask is, what about the remaining piece? What about the modular iterated integrals that where instead of E, we have something that comes from S, from cusp forms? And the reason for looking at that, apart from the sake of completeness or generalization, extensions, and so on, is for what I mentioned before, that generally we expect the more, let's say the deeper arithmetic information, also connected with geometric aspects, elliptic curves, and so on, to come from cusp forms. So that's the hardest, or more elusive elements that we have. So that's the original reason for which it was looked at, this question. So just very briefly, a possible result that one could, let's say, envisage, some kind of dream of, because that's where we are at the moment, it's a bit too early to get into that direction, would be to say, what can we say, given that we have L functions, given that we have period polynomials, can we say something about the, let's say, proportionality relations of critical values of L functions of modular iterated integrals, in the same way that we have Manin's periods theorem and so on and so forth? And the answer is that the qualification is that if you want to even state this question in a meaningful way, you have to move beyond this red space, beyond the subspace of modular iterated integrals that are restricted, that are originating in Eisenstein series. Otherwise, even the question will not make sense. So we at least have some proposal in this recent work of how we could look at how we can pose the question. Okay, so that's the first question. I will show you how it can be addressed. The second question is if we can have a nicer characterization of the space of modular iterated integrals, because if you remember, it was something a bit abstract, reminiscent of logic or set theory, the largest possible space that can have some properties. Is there something more concrete, some kind of different characterization? And the answer is that there is, at least conjecturally, and in some special cases, the cases that actually originate in the studied case of Eisenstein series, it is also proven. You can say that the full statement would be that we expect that modular iterated integrals are linear combinations of iterated integrals of modular forms or their conjugates that conspire to be gamma invariant. So if, in other words, to put it back, if you manage to create a linear combination of iterated integrals of modular forms and or their conjugates, which have the property that as a linear, the outcome of this linear combination is gamma invariant, then you can talk of modular iterated integrals. There is some awkward linguistic thing here happening, that we have the word modular iterated integrals, which has a specific meaning with a definition we already saw. And there is the other one, which is iterated integrals of modular forms. And these are two different things. Iterated integrals of modular forms are integrals nested to each other, which are formed of modular forms, but generally will actually never be invariant, gamma invariant. And we have the modular iterated integrals, which, if you remember, was defined to be the space of a subspace of gamma invariant functions in terms of this action /RS. So you can pass from one to the other by linear combinations. But as I said, in full generality, that's a conjectural definition. So given that it is conjectural, another natural question is whether we can construct explicit families of iterated integrals whose invariant versions will be also explicit for computations, and they also belong to the space of modular iterated integrals. So if we can give some explicit examples of what I described in the previous long sentence, where this passage from iterated integrals to modular iterated integrals can occur. The motivation, one of the motivation for that is, again, in order to be able to make a more concrete analysis of possible arithmetic phenomenon, which I mentioned in question 1 or even before, when we saw that it is likely that there is some arithmetic meaning in this space MIL. So another reason, which is more intrinsic into the originating questions of real analytic modular forms, is that these invariant versions of iterated integrals are exactly those that appear in the context of modular graph functions. And as an example, can give the last section of Francis Brown's papers. It does exactly that, to give explicit examples of iterated integrals, which, if you take their linear combinations of, you end up with modular iterated integrals in the rigorous sense. And then he finds out that they satisfy the same conditions that modular graph functions satisfy. So this question is also important from this non-number theoretic standpoint, if you wish. Now, there is a third question, which is only, I looked upon only at this stage, only because it turned out that this gave the solution to question at least two, to some extent even one. But it refers to another, okay, older, but still not classical object that has been studied, this higher order modular forms. So very quickly, the difference between the difference of second order, for example, modular forms of weight k for a certain group from standard modular forms is that they satisfy more complicated, or if you wish, an iterated version of the classical transformation law. So if, for instance, the standard modular form satisfies f slash gamma minus 1 is equal to 0, it's invariant. Now we do not quite have that necessarily, but we have something more general. We are looking at functions which are annihilated if you apply to that, if you act on that function f by this g minus 1, group element minus the identity element, twice, one after the other. And to make that, this is the only place where I mentioned before, we need this comment about linearity of the action. So what this really means is that we first take f and we slash upon it with gh, then f slashing with g, f slashing h plus f. This must vanish as a function. So this is the characteristic equation. It's not the full definition, but I want to mention what we are referring to. The only now the thing is that here comes the question that the only such forms for the modular group are the standard modular forms. This gives us nothing new in SL2Z. The reason is essentially because they are parameterized in this form, this specific form, by cusp forms of weight 2, which are trivial in SL2Z. So all this theory of higher order modular forms has been developed for higher genus Fuchsian groups, but not for SL2Z. And this is a problem, if nothing else, for practical reasons, because SL2Z has this nice property that you have these two generators, and you can do many things. For instance, a much more clean description of period polynomials, which was mentioned a few slides back. So the question is it possible to, let's say, extend the definition so that non-trivial second order modular forms, especially for SL2Z, can appear? And that's I will leave it at that. We'll see this the answer to this question, and we'll see how the answer to this question leads us to the answer to question 2. But first thing first, now we go to the answers of all those questions. We go to question 1. So to recall the definition, the statement of the question, is what we can say about the modular iterated integrals, which originate in cusp forms, where instead of elements come from E, we have elements come from S. Our answer is to construct in a systematic way an explicit family of modular iterated integrals which do originate in cusp forms. So it gives a recipe, a new type of recipe, different from the recipes that have been used so far in the theory, in order to construct what we want. So the construction in its simplest form, trying to throw away all possible technicalities, is that we start with a cusp form, indeed, weight k for SL2Z. And then we have the Eichler integral of this function, which we denote by capital F. And now, so this line is of course redundant now, because I used to have the also its conjugate, but I wanted to simplify things, not to mention about its counterpart with conjugation. So please ignore this line. It is a typo left over from a previous version. So we consider it the Eichler integral. And now we construct a series, some kind of generalized Poincare series, or to be more precise, a polynomial with coefficients, generalized Poincare series. So what happens here? We act upon, we act on z and x by essentially two different actions. The first one is the action /rs, which we mentioned way back in one of the first slides. And the other one is the classical Eichler action, which we see in the Eichler cohomology. We simply plug in gamma x, which gives us rational fractional transformation. We get some denominators, and then we kill them off by multiplying through with the highest power of the denominator appearing. So we're left again with a polynomial. And we sum over all gammas in this respect, so that we can get the invariance that we require. So the final notation that we introduce in this respect is, as I said before, this is not really a series, but a polynomial which consists of series, or vice versa, series of polynomials. And what we're looking at is at the polynomial coefficients of this polynomial that we get by performing this, what we call sometimes method of images trick. There is a caveat here which reflects the the difference in the actions in terms of x and in terms of z, that we do not take the polynomial coefficients in terms of x, the coefficient of x, x squared, x to the third, etc. But we take something slightly more complicated. We take x minus z bar, and this is going to have some. It is possible to do that. It is an elementary algebraic trick. You are going to end up with specific series of regular functions in Z. So now we pass from polynomial to real, genuine functions in on the upper half plane. So this is this family which is associated to the polynomial phi rs. And so the theorem that we have in this case, this actually encapsulates many theorems, but I wanted to make a point, and so I have merged all those theorems that I proved. We make this assumption, which may seem a little bit ad hoc or innocuous, but it has some nice meaning. So we want the sum of the two weights of the real analytic forms, which was the modular integrals, if you wish, in the end, to be larger than the holomorphic weight k, strictly larger. Then what happens is that in the first instance, we have convergence. Everything that I wrote down makes sense, including the coefficients, of course, that I mentioned. So phi rs of fi, for I going from 0 to k minus 2. And then each of those coefficients, the actual functions of the polynomials, but the coefficients are going to be modular iterated integrals of length 2, which is going to belong to the complement that we were looking for. So we moved beyond the Eisenstein series. So that's the main result for in this case. Now some qualifications or remarks, if you wish. The first point, which again expresses the complexity of the issue. The natural question to ask is, are these phi rs of f I z cuspidal themselves? And the answer is no, and they could not possibly be. They could not possibly be, no matter how hard we tried, we will not be able to find one because they don't exist. When we go into S, this is a more general phenomenon that already was detected by Brown in the beginning of his theory. In order to be able to get such objects, you need to work in the context of meromorphic, of weakly holomorphic forms, or exponential growth of some kind of at most exponential growth forms. This is some work in progress with Frederick Stremberg. We are looking at those objects, again, with motivation, the motivation being that we want to look at the arithmetic. But on the other hand, although these phi functions that I construct in this explicit way are not themselves cuspidal, they do originate in cuspidal forms. So they do project, if you wish, to cuspidal forms, which was the original question. A second remark, very quickly, so they have some time for the remaining questions, is that if you notice the previous slide, I used the word, again, in the very last line of my question answer, modular iterated type. There was a reason for which I put this qualifier type, because there is a small caveat. Again, it is not possible to work in this space if we impose the condition that we remain within the non-negative weights. If you remember, I pointed out that in the definition of the abstract definition of modular iterated integrals, we are looking at the largest space in the, not in the entire curly M, but the algebraic sum, the direct sum of those that have integer, positive or non-negative integer weights. And here we have to relax this this property, because otherwise it would not be possible. So that's the little caveat. But this completes the answer to my first question. And now we go to question 3, not because I don't have time for question 2, which I may not have, but because in order to answer question 2, I need the answer to question 3. So as I mentioned before, we have the second order modular forms, which are trivial in the case of SL to Z, and we need to some construction to allow for genuine second order forms for SL to Z. The construction in elementary form, in reality, what is happening here, we have a tensor product of some representations. But in this case, what we do is we make official the interaction of diverse actions that we already saw in the previous question, and we make that more formal. We have now the action dot, and what we do is we apply gamma, we evaluate gamma, the function of gamma z and gamma x, and then we multiply with gamma z, j gamma z to the power minus k0, and the polynomial usual action. And we are in the, for the time being, in the to begin with, in the space of polynomials of degree less than k minus 2, and coefficients in the holomorphic functions on the upper half plane. This is just to answer the question 3, and then we'll see how we use it to answer question 2. So now we call extended second modular form a polynomial with coefficients in holomorphic forms, which have the property that if you act upon it by gamma minus 1 for a group element gamma, then you're going to have a, if you wish, linear combination of products, one factor of which is a regular holomorphic modular form of weight k, and the other one is going to be polynomials, straight polynomials of degree at most k minus 2, or if you wish, a polynomial with coefficients modular forms of weight k. That's the same thing. And we have also in order to have Fourier expansions, the invariance under only the parabolic elements. This is another condition, more for practical purposes there. So, and now we do have examples, and the examples turn out to be exactly the iterated integrals of cusp forms, but of a more general type than the standard second order modular forms. So examples of that is you take a modular form of weight k, a cusp form of, actually here there is a typo, I meant to say S of k. Let me see something. Yeah, sk, not the nk, because of course we have the infinity. So that's simply a type. And then we take the Eichler integral, the antiderivative, if you wish, of f1. And then it turns out you can prove that you are going to have this property, that if you slash upon it with, or a dot upon it, against it with gamma minus 1, you're going to end up with a polynomial of degree k minus 2, but coefficients modular forms. So in moving on to our context, we can do the analogous thing in our case. We now look at polynomials with coefficients in real analytic functions of moderate growth, of again of degree at most k minus 2. We have our RNS with the usual restrictions, and our new dot function in this context is going to be adjusted accordingly, as we discussed before, that we have two weights, therefore we have to take that into account. But otherwise it's the same thing. And now the definition is again exactly what you would expect: parabolic element invariant elements of the of our polynomials. And now we, on the one hand, allow, of course, real analytic modular forms, but we make a restriction for reasons which I don't think I will have time to explain, that we only specify, instead of all real analytic modular forms, we restrict ourselves to the real analytic Eisenstein series. And the reason is because we want to focus only the case that is appropriate for our solution to question 2. And the reason for which we call them real analytic iterated integrals is because the prototype for such functions, the iterated integrals of real analytic nature. So it will be always some real analytic Eisenstein series times the same object as before, where I again repeat my typo that this should be S and not M. Apologize again about that. So now I am able to complete the discussion with my answer to question 2. It's been a long time since we discussed question 2, and the question is whether we can show an explicit way to move from iterated integrals of modular forms into modular iterated integrals in the strict sense that we discussed, gamma invariant functions, which satisfy this strange definition. And so the question was whether we can do that for some explicit families. And the question 3 will give us the key to do that. So let's go straight away to the answer. We start with one more notation, and we have a cusp form. In this case, I did not do the typo that I did in the previous slides. We have H, which is a weight K cusp form, and we take the period polynomial, actually, I mean, if you wish, for gamma is equal to the involution, that's the period polynomial, or more generally, the image of the Eichler-Shimura map of F. And then we construct, we have the phi function, and now we have the psi function. And here we will need two versions. The first one will be the period polynomial, as I called it, the polynomial, the numerator. And in the denominator, we have what appeared before, but in combination with other actions when we define the phi. So this, again, we have the same construction that we usually have, but we have to be careful because in the numerator, we have something that does not depend on z, but only depends on gamma, and it has the x as well. So it's a genuinely different construction, cannot be accounted for directly by this theory of Poincaré or generalized Poincaré series. There's some kind of twist, if you wish. And as I said, we will need also the conjugate version of that, which is denoted by psi to the minus. So the meaning of the bar is that we look at the complex conjugate with the understanding that as a polynomial, the x stays invariant, is acted upon trivially by the conjugation. It doesn't do anything to x as a polynomial. So now the final theorem, again, it is merging of various theorems. Again, our constraint R plus S is larger than K. And the first statement is that each of those psi polynomials is an extended modular, extended second order modular form. And in fact, it belongs to the space, which I denote in this weird way, of real analytic iterated integrals. That if you act upon it by gamma minus 1, you're going to end up with real analytic Eisenstein series times the Eichler integral of a regular holomorphic cusp form. That's the first statement. So this is the link with question 3, in some backward form, because I was led into that by looking at question 3. The second one, and that's the key, the heart of this of the answer to question 2, is that that there exists a way to start from any element of this real analytic iterated integrals, and then to end up with first of all the elements of MRS, which are in the end, as we will see, modular iterated integrals, and are parameterized at the same time by standard modular forms. And this is a surjective map in a special way. It shows that this psi, the family that we have introduced, is not only an explicit family, but it is a canonical family because it generates essentially the right-hand side of this map. So it expresses all the real analytic modular forms which are generated, of course, by RS. And at the same time, you have the parameterization by the remaining elements. And the final thing, which brings us back to, if you wish, the first part of the talk is that there is a recipe, an explicit recipe, which if I had time I could discuss, that you can go from the space of real analytic iterated integrals, which in turn is generated by the family of psi plus minus, include both sides, and to get modular iterated integrals in this strict sense. So we start with modular iterated, with the iterated integrals of the form that we saw before. That's at the last line. This is what I meant by iterated integrals. In this case, it's a trivial example because it is in length 2 only, but we could have continued this pattern clearly to have iteration. We start from such an element, which we called real analytic iterated integral, because this, and then we, via this construction, by the proof, the proof actually gives the explicit construction, we can go to the family of regular modular iterated integrals, this abstract notion in larger space and so on and so forth, of length 2, and even in a way which characterizes an entire space that arises in a very natural form. So I will leave it at that, and if there are any questions, I have some formulas where some of these things can become more explicit if you want, but they will be left in the slides that I think are usually posted on the web page, but I will leave it at that. This is the answer to question 2. So.
All right. Well, thank you very much, Nikos. Very nice. Are there any? Let's all thank him. Use the react button. Any questions for Nikos?
So you define these period polynomial in general for these kind of classes of modular forms. Are there kind of nice period polynomial relations and say kind of analogs of these results of Zagye and Gangle and Kanako and stuff? Okay.
So yes, so this probably refers to you referred to the first part where I was mentioning period polynomials for modular iterated integrals. This work with Druid, rather, the earlier one. The answer is yes. So what happens is that they have these period relations in the sense that they generate a cohomology group. So you have this the relation that if you act upon it with s plus 1, you get vanishing, or u squared plus u plus 1 again annihilates your period polynomial. But what we do in work in progress is to try to see if maybe we can do better than that, if we could even get something like what you mentioned before, this Manin or Cohen-Zagye relations, where we have L function of 1 divided by L function of 3 will belong to an algebraic field and things like this. We have shown that in that paper with Druid in a special case, but again using this theory. And this was the case of weakly holomorphic modular forms. You can define the L functions there as well. This has already been done before we had this more general context. And then we proved that the Manin's period theorem works exactly in the same form, except for a very nice exception, that the endpoints. So again, very quickly to say what this theorem says. So it says that if you look at the critical values of L functions, L of 1, L of 3, L of I are the same parity, then they are proportionate by an algebraic number, which is even quite precise to define. Now, in this case of weakly holomorphic forms, you cannot say anything at all about these extreme values, L of 1 and L of k minus 1. And this is not because of some kind of weakness of the theory, that if we tried with better methods, we could prove something. But we have checked numerically that there is definitely no normal behavior of those extreme values. Numerically, you can see it's not even computationally too hard. People who know about these things tell me I'm not doing computational things, but it is very easy to see that these values L of 2 over L of 4 is going to be algebraic and all of these things, but you can also just as easily see that L of 1 over L of 3 behaves wildly. So yeah, that was, I couldn't resist saying a little bit more about that because I think it's such an interesting thing. But what we would like to do is to generalize that, to see whether we could prove something like that for all elements of Mi2, or at least for some subspace of that space. But the polynomial is there, we have the basis. And what is very important, and very promising, actually necessary condition to get some arithmeticity is that it's a period polynomial. It is not like a period function like in the case of Louis-Zagi's period functions of mass cusp forms, where they have infinite dimensional spaces. In this case, we get actually polynomials, although the tools in order to construct those polynomials originated in Louis-Zagi's period functions. But somehow they ended up, although we went to a, in some sense, different object, I will not say more complicated, but went to a different object, then we ended up simplifying things, somehow it collapsed into a polynomial. And this means arithmeticity. So there should be something there.
All right. Well, I have a question.
Yep.
Nikos, do you know, I've seen a couple things mentioned recently. This, I know Francis Brown mentioned it, and Zaghi has mentioned it. I think maybe he mentioned it in passing and said he would write it up more somewhere else, but I couldn't see it or something. But do you know much about these quasi periods?
Yes, that's right. Yes. Yeah, this actually, yeah, that is, the quasi periods, like some kind of the dual of the periods that appear in Manin's periods theorem and so on and so forth.
The determinant with regular periods is like.
Exactly, yeah. So this is very interesting actually, because they appear in a very hidden way behind the works in the proof of the theorem that I mentioned before in response to Alexander's question. So just to be more precise, in order to prove that theorem, what we used was some algebraic Derham theorem by Francis Brown and Dick Hayne, and that's where these quasi periods were essential for the construction. They were the heart of the rational structure that gave the algebraic Derham theorem. Now, I expected originally that this would give us actually, give a more complicated theorem, Manin's periods type theorem for weakly holomorphic forms, because I thought it would have doubled the dimensions that are normally appearing in the classical set without the quasi periods. But somehow that's something that I confess I haven't thoroughly understood, what happens is that they simply they play the role of explaining better some two-dimensionality that does appear in the classical theorem by Manning, but it is done in that way in a more perfunctory way, whereas these quasi-forms explain it. But on the other hand, what did not happen, and it was a small disappointment, is that these quasi-periods would appear in an explicit way in the Manning's period theorem of our for weakly holomorphic forms. But they were definitely there. They were like the machine behind the theorem. They were definitely absolutely key ingredients. But what I haven't managed to see how I could factor in, but I suspect, okay, that's just, or at least a hope, is that they will appear in this eventual general Manning's period type theorem. The algebraic behavior, I would not like to call it Manning's period theorem because this restricts it. I would expect that the algebraic behavior will be a bit more complicated. But this algebraic structure of Mi2, I think somehow in a way this quasi-period should show. But I could not, let's say, decouple them from the actual periods in what we have done so far. That's the thing. So,
okay, yeah, I find these kind of interesting. I've seen people do numerical examples of them, and there's some general philosophy behind them, but they seem very mysterious to me, and I don't have
absolutely. Yeah, I agree completely. That's especially because I saw that this is the thing that made things work for me, but I did not know why. I did not know. It did not show anywhere. It's like just something behind the scenes, something which you can't somehow identify. You can't nail down. But I think there is some depth in there which will be found as we move on. But it's amazing. Yeah.
Great. All right. Any other questions for our speaker?
I have just like a short one. This R plus S bigger than K condition, is that just for like convergence issues, or can you still like define things well and you just don't get the structure?
Okay, so I was hoping someone would ask that. Because I had mentioned that this may look a bit technical, but so in the first instance, yes, this is what makes the convergence work, but I'm very confident, maybe I have already done it, that you can analytically continue all those objects. But the reason for which I like it so much is because there was another thing which I simply could not possibly have time to discuss. If you see this theorem 2, where it says there exists a surjective map, we have a much more clear picture of the situation. In this case, we have actually a short exact sequence, and the kernel of this map is also possible to characterize. It is, in fact, some not classical, but vector-valued modular forms that have been studied by people like Jeff Mason, Candelori, by Frank. And now the amazing thing is that I use that in order, I use their theory, the dimensions, give some very general dimensions of modular forms, in order to compute the dimension of this M tilde 2C of R. They could even be extended further. We could get some more spaces thanks to their results, because we have an exact sequence, and then you can use it to have a formula, very complicated, but very explicit formula for this space right here. And now, in order to have this formula, the condition, which is expressed in terms of line bundles, some kind of traces, and so on and so forth. But it boils down to exactly the relation R plus S larger than K. So I have the benefit of that wonderful dimension formula by Candelori and Frank only when I have exactly, not exactly when we require this condition, which is exactly the condition to have absolute convergence, naive absolute convergence. So if we have R plus S larger than K, we have convergence, which is okay, technical thing. But at the same time, down the road, it meets into this other theory of vector valued modular forms. And it tells me that this is exactly the condition that we need in order to have an explicit formula for dimensions. So that's why I say that there is more to it than what you would expect. Because usually people say, okay, that's, yeah, for R and S large enough, I could have said. But no, in this case, this exactly that makes things work.
Great. Okay, may I ask some questions?
Absolutely.
Is K equal to R plus S? Slide 1. And also on the current slide, the last symbol, the theorem 2, there's a direct sum I equals 0 to K minus 2.
Yes.
Mi of 2, where's I?
Yes. Oh, yeah. No, it is said that there are K minus 1 copies. That's the only thing.
Sure.
Yeah, sorry. Yeah, it is the coefficients of this polynomial of degree K minus 1 at most degree.
Thanks.
One last quick question. Have you thought about how this works in the higher level situation? Because I know all of Brown's definitions work in that setting.
Yes. I'm definitely confident it would work, but as Francis had written in one of his earlier papers, he was afraid of the technicalities in that paper. He was concerned that if he focused on higher levels, then the paper would end up in the graveyard of unfinished papers. So this is pretty much what happens here. But there are, I think, that's here I have to be careful, but some phenomena become more clear when you avoid complications due to the level, or avoiding interesting things that occur when the level is higher, and you focus only on these basic things. So it is the beginning of some insight, if you wish. And you want to start with some first set of structure, some first set of phenomena that appear in various structures, and then you work your way upwards. But it made we did go to the trouble of looking at this more general setting of second order modular forms in order to go back and apply everything to SL to Z. So it was a choice at the time, a practical choice. Do I work on gamma 0 of n, where I have ready-made a higher order modular forms theory, or do I extend that theory of higher order forms, and then I stick to SL2Z? And then I saw that somehow it was more practical at this stage to do the latter. And because in any case, there was something, I was curious to see how you can extend this formalism of these. But definitely, I have no doubt at all that everything generalizes to higher level. I don't see any intrinsic reason for any obstacles.
Okay, great. Any other short questions? Well, if not, let's thank Nikos again. All right.